Okay, so instead of going to foundation builder subjective, because like I think it is not of that level, even though it might be. Okay, but the objective foundation builder, it was not of that level. So instead I will be going to get equipped to JEE main directly. So let's start. Uh, yeah. So question number one. In the following equilibria, so K equilibria, first it's K1, then it's K2, then it's K3. Right, so this thing is just 3 times of K first reaction, okay, and 1 times of the second reaction, of course. So yeah, that is like K1 cubed times K2. Right, so K1 cubed times K2, where is it? So it's gonna be D. Okay, question number 2. Naphthalene, a white solid used to make mothballs, have vapor pressure of something at 27 degrees Celsius, has Kp and Kc for equilibria R. So this is the reaction, right? So it's just normal sublimation. Vapor pressure, this thing, Kp and Kc for the equilibria R. So Kp is just the pressure itself, so it's just 0.10 millimeter Hg. But I think we want it in atmospheres. So what do you know? 1 atmosphere is just, I think 1 atmosphere was like 760, yeah, 760 millimeter of Hg was that 1 atmosphere, I think. So then this guy like has actual pressure of 0.1 upon 760. Yeah, for the equilibrium R. I mean, like they didn't give us it like in what units you want this, so we will just say okay, that's the units that we want, right? So but then of course like they have put 0.1 in 2 of these options, and that suggests that Kp is 0.1 and Kc, no, I don't know what Kc is. So its pressure is like 0.1, which is this much of the actual atmospheric pressure. Yeah, that's not good. It's like PV equal to an RT, so P is CRT and C would just be P upon RT. RT in this case, so if you want in terms of atmospheres and stuff, then RT would be P upon 300 into the R would just be 0.08223, whatever that thing is. Right, and since pressure is this thing, this would be 0.1 upon 760 into all of this. Oh, okay. And you can write this thing as 8.2 over there. So you can actually write it as 76 into 3 into 82. So this is like 1 upon 76 into 3 into 82. Yeah, and that is definitely not 0.1. So yeah, doesn't make sense, you know. It might be this thing, 4.22 10 power negative 3. Is this 10 power negative 3? So 76 into 3, that would be 21 and 18, that's 228, and that into 82, it's like 4 5 6 and 0, and that's like 4, right? So 64, 6 carried on, 8 2 6 16, sorry, 16 and 6 is the 22, so 2 carried on, 16 once again, 16 and 2 is 18. Yes, so 6 9 6 8 1, right? This is like approximately 2 0 0 0 0, right? And that's definitely not in order of 10 power negative 3. So it's like looks somewhere near 10 power negative, yeah, this looks more like it. This would be 10 power negative 4 into 1 upon 2, so that's like 0.5. So 5 into 10 power negative 5, that looks more like it. But okay, this doesn't have 5 zeros, that's the problem. And it's slightly more than that actually. You know, this might be correct, but did I miss something? So this thing is 0.1 millimeter of, oh yeah, this is supposed to be 0.1 and not 1. I took it as 1. Then you get this extra 10 power negative 1. Yeah, now it makes sense. So I think C is the way to go. So question number 2, C. But seriously, I have no idea what they want from this. So question number 3. Which one of the following statements is incorrect about chemical equilibrium? Chemical equilibrium is attained whether we start with reactants or products. That's correct. Dynamic nature, yes, that's correct. This equilibrium is attained when this is heated in an open vessel. Open vessel, no, that's wrong, because then CO2 will just fly away and your actual concentration in the atmosphere is very small. So it will like obliterate all CaCO3 and that's not equilibrium. So C is just wrong, right? At equilibrium, the concentration of each of the reactants and products become constant. Yes, it becomes constant. So D is correct, B is correct, A is correct, C is incorrect. So number 4, which of the following statements is correct about equilibrium constant? Equilibrium constant of a reaction changes with temperature. Yes, it does. Correct statements, right? So A is correct. Well, that's it. That's the answer. But seriously, B is equilibrium constant of a reaction depends upon the concentration of the reactants. No. So B is incorrect. C is equilibrium constant of the reaction is whether the reactants carried out in open vessel or closed vessel. Actually, C is in fact correct. What's the problem? No, wait. In an open vessel, this will just be a problematic thing because in an open vessel, there is no equilibrium in the first place. So what does that even make? Like, that doesn't make sense. The equilibrium constant of a reaction becomes double if the reaction. No, no, it doesn't become double. It becomes squared. Okay, question number 5. For which of the following Kp may be equal to 2.9 to the power negative 3 atmosphere? Hey, look at the units because they didn't give any values. So just look at the units. It's atmosphere, and yeah. So 3 plus 4. Okay, that's gonna be 4. 4 minus 2 is 2. So that's gonna be atmosphere squared. Not good. This thing has no. It's not good. This has atmosphere to the power of 1 upon 2. That doesn't work. D works. So question number 5D. Question number 6. The value equilibrium constant for an endothermic reaction. So it increases with increase in temperature. Yes. It decreases with a decrease in temperature. Yes. Endothermic reaction, right? So yeah. Is independent of temperature? No. Sufficient information is not. Okay, so A and B both are correct. But is this a multiple choice? For an endothermic reaction, right? So A and B are both correct. Is this a multiple choice question? I don't know. It's not independent of temperature, of course. So A and B, I'm just gonna go for both of them. A, B. Number 7. Value of K for this reaction. 2A gives B plus C. Okay. Is this thing the value of K at 750 Kelvin and 20 atmosphere? Just changing the pressure doesn't change anything, you know. So it's still the same thing. So 2.86. So C. Right? Yeah. Question number 8. Consider the following equilibrium in gaseous phase. Vapor density is smaller than theoretical value in case of. So vapor density, that being smaller, that just means the actual mass. Well, the actual mass, of course, just remains constant. So the actual mass upon the number of moles, that's the molar mass, and that upon 2 is the vapor density. So vapor density being smaller than theoretical value, that just means the number of moles is more than what we expect them to be. And for theoretical value, of course, like yeah, theoretical value of which of these gases in this reactions, I think the one which are decomposing. So PCl5 again PCl3 plus Cl2. The number of moles increases, of course. So yeah, like its density will decrease. What's the okay? Second, yeah, the same thing. Third, also the same. Wait a second. Third, what is this? What's going on over here? CH3COH gives CH3COOH. Okay, two of that. Oh, okay, so this is like forming some kind of dimer over there. Oh, so in that case, the number, like, yeah, it actually decreases. So only 1 and 2 have vapor density smaller than theoretical value. So there we go. This is option number 8. Which oxide of nitrogen is most stable? Okay, so you gave the Kc values for all of these. Uh, huh. So the yeah, like your K value that is actually related to your delta G value, and delta G is related to spontaneity, right? So delta G standard, that will be negative RT natural log K. Yeah, and for the equilibrium constant, you would just have the concentration of these guys upon the concentration of N2O5 and stuff. So, I mean, of course, you just have Kc as the thing that decides your delta G. You don't need the concentrations actually. So once you know what your delta G is, you can find out spontaneity in different temperatures and stuff, right? Because you know what delta G standard is. From that you can figure out different things. Okay, so which oxide of nitrogen is most stable at some like very high temperature, right? So are these cases for this temperature or what temperature? I think these are for that temperature. They can't be for the STD. Sorry, STP. Right? Because how would you even convert from there to there? Right? that cannot happen. So, yeah, like so. For these C and B, you need to divide by 2 because you are decomposing 2 of these. Then that's not what we want. We just want decomposition of one of them. Oh wait, but then you also have this N2O5, so it's actually got 2 moles and stuff. So sorry, 2 nitrogen atoms and stuff. So yeah, how would you even compare stability? It's kind of a problematic thing actually. So then delta G is different for each of these. You know that delta G is just negative RT natural log Kc, yes. And what does that value actually tell us? Tells about the spontaneity, of course, but in a qualitative sense, not in a quantitative sense, you know. So the most stable, what does that mean? I don't know. I don't know. Yeah. Fine, you just compare the values. That's it. That's what we'll do. So they only give the cases. So this is smaller, this is bigger. So A is more stable than B. Sorry, A is more stable than C, and A is less stable than B. And oh, so D is the most stable because 10 power 15 is that. No, wait, it's got only NO2, so you should actually do twice of that to have a good comparison. And for B as well, you should actually have half of that. So half of this reaction, that will actually give 10 power 16. And this would actually be 10 power 30. So yeah, in fact, B is the most stable with that logic. Though I don't know if that logic actually works. Number 10, starting with 1 mole of O2 and 2 moles of SO2, the equilibrium for the formation of SO2 was established at certain temperature. If V is the volume of the vessel and 2x is the number of moles of SO3 present. The equilibrium constant will be, okay, 2x is the number of moles of SO3 present and 1 mole of O2, 2 moles of SO2. The reaction is something like this, right? Yeah. Content process. So this is 1, this thing is 2, and then it changes. So this now becomes 2x. So it's 2 minus 2x over here. This is 2x over there, right? at certain temperature. V is the volume of the vessel, so this thing upon V, that's the concentration, equilibrium constant, so Kc of course, and that will just be this thing, SO3 over there. Hey, but that being SO3 means this should be half, because yeah, right, and then it's just square root of that. There's no square roots over there, so actually it should be like O2 plus 2 SO2 gives 2 SO3. That means this is going to be squares. Okay, so this upon that will be x squared upon 1 minus x squared, and then that thing upon O2. So O2 has activity 1 minus 2x upon V. V goes on the top, so Vx squared upon 1 minus x complete square times 1 minus 2x. Hey, this should be, yeah, actually it's correct. Right. Why did I square? Yeah, it should be a square over there. Right? It's not 1 minus x cube. It's not these things. Well, there's no volume over there. No, not. Oh, hey, 1 mole of O2. Oh, and for this reaction, actually, if you have 2 of these, then it's just x of that. Oh, then it makes sense. And this should be 1 minus x. So yeah, the first is the correct. So 10A. Question number 11. Formaldehyde polymerases to form glucose. According to this reaction, the theoretically computed equilibrium constant for this reaction is found to be this thing. If 1 molar solution of glucose dissociates according to the above equilibrium. Right, so for the reverse reaction, your equilibrium constant will be different, right? It will just be inverse of that. So 1 mole solution of molar solution glucose dissociates according to the above equilibrium. Concentration of formaldehyde in the solution will be, right, so it's going to be 6x upon 1 minus x, and this is going to be 10 to the power of 6, right? That will be 1 upon 6 into 10 power 22. Right. The concentration of the formaldehyde in the solution will be. So just need to find what 6x is, and we'll be done. Okay. So look at this. I mean, this is like x power 6 upon 1 minus x is 1 upon 6 to the power of 7 into 10 power 22. Look at this number. It's huge. And so what this equation actually tells is that x power 6 is this, like 1 minus x upon all of that. But 1 minus x is of course less than 1. So this thing is less than 1 upon 6 power 7 to 10 power 22. That means x is less than 1 upon 6 power 7 upon 6 into 10 power 22 upon 6. And that is still very small in comparison to 1, right? So 6 power 7 upon 6, that is something bigger than 6, right? And 10 power 22 upon 6. So 22 upon 6 is it's bigger than 3, of course. So it's like 10 power negative 3, but even less than that. So it's obviously it's much less than 1. So you can kind of ignore this 1 minus x over here, and this would be the thing. So 6x, our concentration basically, that thing, hey, 1 molar, right? So yeah, that's how it should be. So c power 6 is just 1 upon 6 into 10 power 22. So just want the 6th root of this thing. Oh no. 6 power 22. You could write this thing as 100 upon 6, and then it's like 10 power 24. 100 upon 6, the 6th root of that. What's 2 power 6? 2 power 6 is 64. 100 upon 6, that is, no, that is like 1 and 40. That's 16 point something. Oh, 16 point something. No, that won't work. Or who knows, it might work. So 1 power 6 is just 1, 2 power 6 is 64, 3 power 6 is 729, near to that. 600 is close but not close enough. 4 power 6, that's huge. Okay, that's gonna be 64 squared and whatnot. Right, it's like 2 power to power 12, that's 1024 times 4, which is 40. Yeah, so whatever that is, like, yeah, 409 something, so whatever. The thing is, it's very big, and it's not matching with anything. The closest we can get is, of course, a 64. With a power of 6, that's a bad thing actually. So like 100 upon 6, that's approximately 16, of course, because 96 is close enough to 100. So like, see, we can technically write this as cube root of 2, because no, sorry, cube root of 4, because square root of, yeah, upon 10 to the power of 3, right? So cube root of 4 is like 1 point something, and 10 power negative 3, that's the big thing about it, that 10 power negative 3 should be there. And that's not in the options. Come on, seriously. Now what went wrong? 16, okay. Something actually bigger than 16. So cube root of 4, it's definitely just bigger than 1. 1.6. Oh god. 6th root of that, that's just the cube root of 4. Okay, and that's 10 power negative 3 over there. How does this not make sense? Right, we can definitely just ignore that. So it should be just that thing with power of 6 upon, but this guy's concentration didn't change much, so it's still 1. Yeah. Concentrated formaldehyde in the solution will be, like, come on, that's not fair, because it's just the 6th root of this thing, and that's this value. How does this not be in the option? 6 times of that. Okay, we don't know, so just leave it. Something's wrong. That's all we can say. Something's just wrong. Oh wait. Sorry, this should not be 3, this should be 4. Sorry. No, nothing's wrong. This is supposed to be 24 upon 6, which is 4. So this is actually 10 power negative 4. Then 11p. And there we go. 11b. Next question. Number 12. What time is it? 6:07. I started at, I don't know. I don't know. Number 12. A liquid is in equilibrium with its vapor at its boiling point. On average, the molecules in the two phases have equal Gibbs energy, of course. And the like entropy is different, I think. Equilibrium with its vapor at boiling point. Intermolecular forces, maybe, no idea. But it can just leave, right? So the liquid can just kind of leave the surface and go into the gas phase. That means its kinetic energy probably is what we are talking about. Its kinetic energy must be, I mean, at least the molecules on the surface, those must have the same kinetic energy as that in the gas. I think so. So potential energy, intermolecular forces. So when you have both energy and potential energy combined, maybe that makes sense, because there's no potential energy for a gas. There is potential energy for a liquid. So if you want to pluck out those molecules, you have to work against these molecular forces. For that, you need heat. So the kinetic energy of the leading molecule, that must be more than the kinetic energy of gases, of the gas molecules. So yeah, this will make sense. Potential energy on, it's definitely not the same intermolecular forces. And what does D imply? Does it mean kinetic energy plus potential energy, or does it mean, I don't know, I'm just gonna go with the thing that seems more intuitive. I'm gonna go with C. Right. So if there's no like cohesive forces acting on it, then it's okay. But then if there's no cohesive forces, there's no liquid in the first place. So just keep on going. When two reactants A and B are mixed to give product C and D, the reaction quotient Q at the initial stages of the reaction. It's pretty big. I mean, like it's bigger than the equilibrium constant, of course. So it decreases with time. Yes, it does. Is it independent of time? No. Is zero? No. Uh, wait. The reaction quotient. Sorry, it's less than K and it wants to be big so that it gets close to K. Yeah. Sorry. That means it increases with time. Yeah. So it should be D, and initially it is zero because there's no products. Hey, these are mixed with no. There's no products. Yeah, initial stages there's the product. So it's zero, and it does increase with time because yeah. So A and D. Question number 14. Increasing the pressure for the following equilibrium result in the formation of more H2O. Oh yeah, this thing. We just did this kind of thing. So you know that this is actually well known because the vapor pressure of H2O that is kind of a constant at a certain temperature. So when you increase pressure, your vapor goes back to liquid, so that your pressure now becomes once again what it was previously. So increasing the pressure will result in more liquid. Formation of more H2O liquid, yes. Formation of more H2O gas, no. Increase in boiling point, no. No. Wait, actually, yeah, like changing the pressure does change the boiling point because now you have changed the pressure. Uh, but wait, isn't boiling point defined as the point at which the pressure is the atmospheric pressure? Yeah, and then it doesn't make sense. Okay. Hmm. Oh, okay. Probably it means like when you're boiling, there's just this vapor pressure and nothing else. There's no other gases over there. Okay. So what does increasing the pressure do to boiling point? I don't know. Increasing the pressure of the piston. What will that do to the boiling point? Doesn't make sense, right? Because boiling point is defined by pressure. So changing pressure just does everything incorrectly. Ah, no, I have no idea. Like, what is boiling? Why did this happen? Why is this? Just wait a second. Ah, come on. What went wrong? That's gonna take forever. Okay, so okay, we are back. Sorry for this interruption. Right, question number 14, right? Uh, so it will definitely be 1. It forms more H2O. And it is in okay, we don't know. So 1 should be there, and it's in it's in A and C. So which have either 2 or 3 formation of more. So like this is just wrong. A is just wrong. And in that case, maybe C. Oh, there's also D. So one of these, huh? Huh. I'm gonna go with it increases the boiling point because I feel it is intuitively correct, even though I have no evidence to support it. Yeah, the problem is we don't know what boiling point is. Like for standard pressures, we understand what boiling point is, but for a changed pressure, what does that mean? I think it just means again, I have no idea. I have no idea. It's not just the equilibrium because we are already at equilibrium. So yeah, I'm just going to go for third. So 14C. Consider the following gas phase reaction which affects neither the composition nor the value of Kc. Okay, so addition of reactants, catalyst, helium, which affects neither the composition nor the value of Kc. So only D doesn't, only D affects Kc. Everything else is just like normal. Wait, neither the composition. Oh, then the equilibrium should not shift. Okay. Delta is positive and stuff. Okay, so changing temperature of course changes everything. Addition of catalyst, it doesn't change anything. Addition of reactants, and okay, that will change everything because it changes the composition. Addition of helium, so this thing is actually dependent on the pressure, and if you're constant, like if you're doing this in a constant pressure environment, then yeah, addition of helium will change everything. So C is the way to go, I think. In the lime kiln, the reversible reaction proceeds to completion because of this reversible reaction proceeds to completion. Because of yeah, sorry. So it's because of the CO2 removal, of course. So CaO is removed now. CO2 escapes, right? What else could be the thing? So I think it's B. Question number 17. For the following reaction is equal to 4 at certain temperature, what concentration of NaCl must be put into a 4-liter vessel, okay, reaction vessel at the start in order that the equilibrium concentration. And what's the time now? 6:16. So yeah, I'm going fairly good, fairly fast. Okay, whatever. For the following reaction, Kc equal to 4 at certain temperature. Okay, and what concentration of NaCl must be put into a 4-liter vessel at the start in order that the equilibrium concentration of NaCl will be 1 molar. So you have NaCl, then you have NO, and you have Cl2. Yeah. So initially you just have 4. No, you don't know what the concentration is, right? So you know the Kc is 4. Initially concentration is just C. Okay. You don't know what these are, right? Then once again, why is this going off? Okay, fine. This won't let me go in peace, will it? Okay. So after this, so from this reaction you have 2x and x, and this whole minus 2x. So it's going to be C minus 2x, and C minus 2x is what, like 1, right? Equilibrium concentration of NaCl is 1, so this is 1. So we know that this means 2x, okay, no, 2x to the power of, so if NO is 2, so 2, and then x, just x upon NaCl squares, like that, just 1. That thing is equal to our Kc, which is 4. There we go. That means x is 1. Putting x 1, just becomes 2 and 1. There we go. And this thing is C minus 2. So C minus 2 is 1, C is 3. Got it. Right, 3 molar. B. Next question. The vapor density of N2O4 at certain temperature is 30. What is the percentage dissociation of N2O4 at this temperature? So it's 30. Okay, that's weird. What is the dissociation? So if you got, let's say you just talk about 1 mole of N2O4. Yeah, I'll just skip this in fact. Right, so vapor density of N2O4. So we are assuming you just have N2O4 in a vessel initially, and then it dissociates, and then you find the mass of that and the moles of that by doing some pressure calculations. Yeah, and then what is the percentage dissociation of N2O4? Cool. So the apparent vapor density, that is just the mass of the reaction mixture, which is, so initially you had say N0 moles. So N0 into the molar mass of N2O4, okay, upon the new number of moles, which is N0 into, so N2O4 dissociates into 2NO2, and that means it's like if it initially had N naught, then it's going to be 1 minus alpha N2O4 and 2 alpha and not NO2, so it's going to be 1 plus alpha, right? It cancels. Oh, 2 times of that's like, yeah, so vapor density times 2, that's just the molar mass. So it's going to be 60 over there. Okay, and what is M? So it's going to be 2 times of NO2, mass of NO2, 1 plus alpha equal to 60. So this is just 30 once again. And NO2 is 14 plus 2 into 16, which is 32. And that is 46. Okay, so 46 upon 1 plus alpha is 30. Okay, that means alpha is 46 upon 30 minus 1, which is 16 upon 30. There we go. Right, so you got it. Now you know what alpha is. So what do you want? You want the percentage dissociation. So now we have alpha, percentage of that. It's going to be 160 upon 3 percentage, which is 5 and 5, 3.33, so on. So A. It's supposed to be D, I think. Okay, next question. Question number 19. What are the signs for delta H, delta S, delta G for the freezing of liquid water at -10? So freezing is always it's always exothermic because we need to take out heat. So delta H is positive, and these things C, B, so C, B, D are just neglected directly. So delta H positive, delta H is positive. Yes, delta S is negative because water has more entropy, I think. So yes, and delta G is positive because at -10 degrees Celsius. Wait, what? Delta G being positive, that doesn't make sense. Like freezing of liquid water, right? How can delta G be negative? How can it be positive? It should be negative. Wait, what? That doesn't make sense. Delta H must be positive because it's endothermic, and the change in the enthalpy is. Oh, no, wait. It's exothermic, of course. What am I saying? I just said it releases off heat. It's exothermic. You need to take off heat from it. So it's exothermic. So delta H must be negative. And delta G must also be negative for this reaction because it does happen. So yeah, and delta S is also negative because water has water has more entropy than ice. So D is the way to go. Question number 19. Question number 20. Consider the following reaction at equilibrium at a total pressure that we will call P1. Okay. Suppose the volume of the system is compressed to half of its initial volume, then the equilibrium is re-established. The new equilibrium total pressure will be. So the volume of the system is compressed to half its initial volume and new equilibrium is re-established. Initially it was at some pressure P1. Now we just changed, like, okay, why compressed to half of its initial volume, right? Yeah, so the volume does play a role. This is not good. So you can definitely write Kp in terms of okay, the mole fractions, we don't know what the mole fractions are. That's not good. Equilibrium is re-established. What about the pressure? Does the pressure change? Of course it does change, and the number of moles will also change because your volume just changed, so your Kc must be the constant. And yeah, so what's it like? It's like number of moles of SO3 upon V squared upon number of moles of SO2 upon V squared, right? And number of moles of O2 upon V naught squared. This will cancel, this goes on top, so it's proportional to volume, right? Your reaction quotient is proportional to volume, and this is equal to Kc. That means this is the way it goes. Yeah. So when you when you increase your volume, now you decreased your volume. So this right hand side just became 2 times of what it should have been. Yeah. So this quantity must also have become 2 times of what it should have been, right? Okay, so SO3 increased, SO2 and O2 decreased. Okay. How do we do it now? Do we assume that these are actually in the ratios as given in the stoichiometry, something like that, like SO2 and O2 are in those particular ratios or something like that? So the new equilibrium at total. Okay. Hmm. Come on, think about it. Its volume is half. Yes, I understand that, right? This quantity just became 2 times, and well, you could do a similar thing for like Kp as well. So you could just, instead of having volume over here, you just have Kc upon the total number of moles, right? So n total, and yeah, actually Kp upon n total, right? And there's this pressure over there, so pressure upon n total, and that's why actually no, n total upon pressure. So there's this pressure goes over here, that's equal to whatever this thing is, so it's the same. Oh, hey, that's nice. Wait, but we don't know how n total changed, do we? Total pressure changed, the n total also changed. And how did it change? The volume changed to something. Your n total does change, no? So P3 P1 less than, oh hey, maybe D could be, so when you suddenly increase your pressure, so now when you instantly just compress it, it becomes 2P to be 1, and then after that, because its pressure is so high, it will shift to right, and that will decrease its pressure, so it's definitely less than 2P. That's it, it's less than 2P1. We don't know if it's P1 or not, but it is definitely less than 2P1. So D is the way to go. I should have seen that option first, so I could have solved everything for me. Question number 21. Okay, xy2 dissociates as xy2 gives xy plus 5, and the initial pressure of xy2 is 600 millimeter of Hg. The total equilibrium pressure is this. Okay, for the reaction, assuming that the volume of the system remains unchanged. What? The total equilibrium pressure is 800 millimeter of Hg. Oh, K for the reaction, assuming that the volume of the. All right, right. Right, so initially it was 600 millimeter Hg, that was your xy2, and its so volume of system remains unchanged, and then it just goes to xy. Okay, I get it. And total equilibrium pressure is 800. So 600 times 1 plus alpha is 800. Alpha is just 8 upon 6 minus 1, which is 2 upon 6, which is 1/3. Alpha is 1/3. Right. So 1 minus 1/3 is 2/3. So xy2 just became xy2. It just became it's like what, 600 into 2/3, which is 400. Okay, and the remaining thing is like xy is 1/3 of 600, which is 200, and this thing y is also 200, so it adds up to 800 perfectly. And then Kc is just 200 times 200 upon 400 square, so you could just write this as 1 upon 2 square, because 200 is a common factor, so you can just get rid of that, so it's 1/4. That is your K. Both Kc and Kp, same thing. So yeah, it is 1/4. Hey, what? K for why is this like okay? Oh hey, millimeter Hg. That's the problem. Millimeter Hg is not something that we want to deal with. So we want to convert from that to atmospheres. So we will divide this thing by 1 atmosphere, is just 760 millimeter Hg. So this is upon 760. And it's not square. Oh shit! It's not square. It's just that. Oh, this cancels. Why did I square that? There was no reason to do it. So this now just becomes 100 upon 760. There we go. Huh. Or you could write it as 100 millimeter Hg. But no, like you don't want in millimeter Hg. You want in atmospheres, right? So it should be this thing, and that is definitely not 100. Okay, we'll just have to go with 100. I don't know from where do these people have these like weird conventions, but if they want in millimeter Hg, we'll put in millimeter Hg. Okay, question number 22. If for this reaction Kp is total pressure, okay, and starting the dissociation from 4 mole of A to B. Kp is total pressure at equilibrium. And starting a dissociation from 4 mole of A to B. Okay, A to B. What is this? A2 and B2. So 4 moles of this, 4 minus 2x, it will be 2x over there, this will be x over there, right? Kp total pressure. I don't understand this. Oh, so okay, this is an equation that we have to solve for. Okay. Starting a dissociation from, right? Fine, understood this. So this being the total pressure, yeah, like when does that happen, huh? So the mole fractions, that will be x upon. We could write it in degree of dissociation as well. Okay, what do you want? Where is it? Question 22. Degree of dissociation of A to B. Total number of moles. Correct. Find degree of dissociation basically. So you start with 4. 4 into 1 minus alpha. This will be also alpha because yeah. And sorry, 4 alpha. And this will be 2 alpha. Yeah, it's half of that. Right. And that means 2 alpha times 4 alpha is like 8 alpha squared upon 4 into 1 minus alpha. Oh wait, no. Square of that. So 2 alpha times 16 alpha squared upon square of that as well, so like 16 minus 1 minus alpha squared. So this is going to be 2 alpha cube upon 1 minus alpha squared. This thing is our Kp. Sorry, it's not Kp. You also need that pressure upon all of the. Okay, so instead of, so it will be just 1 pressure upon total number of moles thing. Sorry, pressure upon the addition stuff. Yeah, and that will be P upon, so addition of these two, addition of all of these. Yeah, total number of moles. You need that, of course, you need that, right? Because it doesn't cancel by itself, does it? So this will be 4 plus 2 alpha. That means P upon 2 plus alpha into 1 minus alpha squared alpha cube. This thing is, what is this? It's the same thing as P. Oh yeah, that this cancels. So alpha cube is 1 minus alpha squared. It's like same thing as alpha minus 1 squared. So alpha squared minus 2 alpha plus 1 times alpha plus 2, which is alpha cube minus 2 alpha squared plus alpha plus 2 alpha squared minus 4 alpha plus 2 cancels. Hey, that's nice. And this just becomes negative 3 alpha Okay, this is plus 2, this cancels as well. So alpha is just 2 upon 3. Right, that's it. Alpha is 2 upon 3. We got it. So degree of dissociation is 2 by 3. So A is very correct. Total number of moles of, okay, at the equilibrium. That will be this thing, 4 plus 2 alpha, which is 4 plus 2 into 2 upon 3. 4 plus 4 upon 3, that is 12 plus, yeah, it's 16 upon 3, not 14 upon 3. Okay, at equilibrium, the number of moles of A to B are not equal to the number of moles of B to. Number of moles of A to B, that will be 4 into 1 plus alpha, which is 4 into 1/3, so it's 4/3, and B2 is also 4/3. Yes, so these are equal. So C is wrong. At equilibrium, number of moles of are equal to number of moles of A2. Yeah, so this will be different because it's twice of that. So yeah, there we go. A is the way to go. Question number 23. Le-Chatter's principle is not applicable when H2O, okay, react to form 2H. I mean, it is applicable. It's just that we cannot decide on which of the two sides to go because both are the same. PCl, okay, this is applicable, of course. Right, so D, in D it's definitely not applicable because, yeah, it's in solid state. So 23rd, D. Question 24. Right, dilute HCl is added to the following equilibrium at constant temperature. Okay, the concentration of this guy will increase. So when you add H plus, basically Cl, like HCl just completely dissociates to H plus and Cl minus. So you are adding H plus basically, and that will revert back this reaction. So concentration of CH3CO minus will decrease, and yeah, equilibrium constant will increase. Okay, fine. So B, question 24B. Question number 25. Which of the reactions will be favored at low pressure? So low pressure, that means favored at low pressure. When it's low pressure, you want to increase pressure, right? Yeah. So this should have a higher pressure in that case. So a higher number of moles. So this doesn't work. A is just unaffected. B is unaffected. C is, yes, it's correct. At lower pressure, we will go to the right side. And D, no. So C, 25th C. So 26. Which one of the following reactions is favored by increase of temperature? So this is plus something is exothermic. No. No. Yes. No. So B. Question number 27. Increased temperature favors the forward reaction. Oh, so there's no delta H given. We have to go from memory. So C, graphite to diamond. No idea, man. SO2 to SO3. You can kind of go for entropy and stuff, I think, but it's seriously just delta H that we have to go for, and we don't know that, do you? Yeah. 2O2 gives 3O2. Oh, this thing, we know that ozone is of higher energy. That means this actually is an exothermic reaction. So B is eliminated. D is it's combustion, right? So it's exothermic as well. So no, D is also eliminated. A, I think SO3 is more unstable or something. So maybe this is going to work. And graphite to diamond. Huh. Yeah, like diamond is very stable because it's so hard to combust. Isn't that correct? Graphite is also hard to combust. So how am I going to do this? Which of them has higher energy? I think diamond is more stable. So then this is also exothermic, right? This might also be exothermic, of course. And in that case, A is probably the only endothermic reaction because SO3 is probably like unstable. So I will go with question number 27. Like when you dissolve SO2 in water, it doesn't give off a lot of heat, does it? When you dissolve SO3 into water, it does give off a lot of heat because it forms that concentrated H2SO4, and then you keep on diluting it. So yeah, but yeah, of course that involves H plus over there, so we don't know. I'm just gonna go with that. 1 mole of helium is added to the dissociation equilibrium. Helium, okay, so N2O4 gives that. Set up in a cylinder fitted with, right, the kind of question that I was talking about. So that the distance of this move out to keep the pressure constant. Right. So the thing is that the actual pressure of the system that will decrease. So it will try to go to the right to increase the pressure. So the equilibrium will shift in a forward direction. Yes. So A, 29A. Where's 28 though? Oh, we didn't do it. 29. 28. The oxidation of SO2 to SO3 is an exothermic reaction. It's an exothermic reaction. Hey, is that really the case? It's an exothermic reaction? How is that? Okay, so if that's the case, then the yield of SO3 will be maximum if... Man, this is weird. The temperature should be minimized. And then this is wrong. Solution 27A, can't see anything for sure. So the option that's remaining is C, because yeah. So graphite to diamond. I like this might be endothermic, who knows. Diamond is less stable than graphite. No idea why that is the case. Okay, the oxidation of SO3 to O2, sorry, by O2 to SO3 is an exothermic reaction. The yield of SO3 will be maximum if temperature is reduced, and so pressure must be increased so that it shifts to the right. Right, so question number 28 should be B, I think. Okay, cool. Next you have 30 Ostwald's process for manufacture of nitric acid involves the reaction Ostwald's for manufacture of nitric acid involves this reaction. Delta H is given. Which of the following factor will not affect the concentration of NH3 at equilibrium? So it's got NH3 plus O2 gives NO2 plus H2O. So then like amount of H2O is irrelevant. 4 plus 5, and that gives 4. That means if like yeah, higher pressure will favor the forward direction. So okay, delta H is also positive. Yeah, so temperature changes are also there. Anything else? No. Yeah, addition of catalyst, it doesn't favor the concentration of H3 at equilibrium. So D. Hey, question number 30, we did it. So question 31. At 30 degrees Celsius, Kp for the dissociation reaction is given. If the total pressure is 1 atmosphere, the degree of dissociation of SO2Cl2. Assume 1 minus x squared is approximately 1. Okay, so like what that means is like if the degree of dissociation is say x, then what you are saying is it doesn't actually dissociate a lot, and it's just SO2 and Cl2. Oh, that actually is like okay. Total pressure is 1 atmosphere, so the mole fraction is approximately 1 for SO2Cl2, right? So you could just write it like that. It's almost all of the pressure itself, and for SO2 the mole fraction is like what do I say? It's like 2x plus, no, it's not x, it's just x, not 2x. X upon 1 because it didn't change much. So yeah, x times p. That's the partial pressure, and that thing times x of p for that guy as well. Right. It's like x squared times p is approximately your kp. Where is question number 31, right? So your kp is 2.9 to 10 power negative 2. Right, and your pressure is 1 atmosphere, so you can get rid of this. In fact, the degree of dissociation is like the square root of this thing. So it's 10 power negative 1 times square root of 2.9, which is like 1 point something, I think. And yeah, and the percentage of that would be 10 times square root of 2.9 percentage. So something slightly bigger than 10. So it could be 1 point, okay, it could be 17% or 13%. Which of these are we going to go for? So 2.9 square root of that is like approximately square root 3, which is 1.7 something. So C, I think that's where we should go. C. Question number 32. 3 moles ammonia is heated in presence of 1 mole of neon. At equilibrium, the mole fraction of hydrogen is found to be 0.5. The value of Kc into V for NH3 gives 3 mole ammonia, 1 mole neon. Okay. Mole fraction of hydrogen is found to be, so involving neon as well. That's not good. Mole fraction of hydrogen is found to be, so nothing about the pressure is given, right? Huh. Oh, so you do know something about the volume. Okay, fine. Kc times volume. So the thing for this is like it's delta and gaseous. It's just, so half plus 3.2. It's gonna be 4 upon 2. So 2 minus 1 is 1, and that means it has that 1 upon volume thing over there. So this thing is actually just NH2 to the power of 3 upon 2, and then N2 to the power of 1 upon 2 upon number of moles of NH3 to the power of 1. So that's actually what we are looking for. And okay, 3 moles of ammonia, 1 mole of neon. You just want to figure out what this thing is. And yeah, fine. This is NH3, this is N2, this is H2. You have ammonia, so for ammonia it's, what? Neon, 1 mole. So say H2 is like 3x, this is x, this is this minus 2x. So total number of moles, that thing is 4 plus 2x, right? So 3x upon 4 plus 2x, that's the mole fraction of H2, and that is 0.5. So we can find x from that. Cool, this is 1 upon 2 basically. That means 3x is 2 plus x, and 2x is 2, so x is 1. Cool. This thing is 1, this thing is 3, and this thing is 1 now. Got it. So now we can find that out. So n2 to the power of 1 upon 2. So 1 square root of that is 1. Then 3 to the power of 3 upon 2 upon NH3 or whatever power, just 1, right? So it's 3 to the power of 3 upon 2, which is basically 3 square root 3. So C should be the thing. Question number 33. The vessel, okay, a vessel at something temperature contains CO2 at pressure 0.5 atmosphere. Some of the CO2 is converted to CO on addition of graphite. The value of K if the total pressure at equilibrium is 0.8. So I think K is just for equilibrium, right? Total pressure at equilibrium is 0.8. Initially pressure was 0.5, and it's a vessel, that means volume is constant. So number of moles is proportional to pressure. Right, so what's the deal? Carbon solid, this is graphite, this is graphite, plus CO2, that gives 2 CO. And this is like 0.5 minus X, so some loss of pressure, and it's got 2 times the moles, right? And that's why it's 2X over there. Right, and add that up, so like 0.5 plus X, that thing is 0.8. So X is 0.3, got it. This should be 0.2, and this should be 0.6. So what do you want? What the value of K? That's just this guy squared, so 0.6 squared upon 0.2, which is 0.6 times 3, which is 1.8, I think. Yeah, 1.8. So A, 33A. Question number 34. Ice and water are in equilibrium at 273 Kelvin. 273 Kelvin? Yeah, that's just 0 degrees Celsius. Of why am I thinking too much? Which of the following statements is correct? G ice is bigger than, okay, that's, so C is of course is equal to 0. Does that even make sense? You know, entropy, like entropy as a function itself, that's kind of weird, because how can you find entropy, how can you define entropy uh, just, you know, just based on the state that the thing is in? That's just impossible, and that's why I think D is the way to go. So question 34, D. And they did say it's not equal to 0. That's also a strong statement. They should have said we don't know anything about it being 0 or not. So just Gi is equal to GH2O, but they didn't. But yeah, that's how it should be. It's D. So 35. Consider the water gas equilibrium reaction. Which of the following statements is true at equilibrium? Oh, water gas. That's just CO plus H2. Okay. If the amount of carbon solid is increased, while less water would be formed. No, it's irrelevant. More CO and H2 would be formed. So it's an equilibrium already, so you don't have to worry about amount of graphite. If the amount of, okay, whatever. If the pressure of the system is increased by halving the volume, more water would be formed. So pressure increased, it would revert back, and that's why more H2O would be formed. Yes, that's correct. If the pressure of the system is increased by having the volume. Okay, no, D is incorrect, so C is the way to go. Cool, let's check. So now we won't be getting that. Okay. So first D, second C, third C, fourth A, fifth A and D. Okay, we'll see what that is. Sixth A and B. That's right. Seventh C, eighth A, ninth. It's D. Okay, it's wrong. It's supposed to be D. Fine. Question number 10A. What's this? Question number 11, D. Then C, D, C. So A is not correct and D is correct. We'll see what went wrong. 13 is only D. So 14 is C. Question number 15 is C. Question number 16, D. Question number 17, D. Then A. Then D, D. Then B. Question number 22, A. Question number 23, D. Question number 24, B. Question number 25, C. Yeah, it's going right. Then what's this? 26, D, C, B. Yes. 29, A, D, C, C. And A, D, C. Yes, that's one correct. Okay, so we went wrong at this and at this and at this. Right, let's see. So go up. That's advanced, I think. Yeah, that's advanced. Okay, so for mains, first we want question number 5. So they gave A as the answer. So equilibrium constant of a reaction changes with temperature. So which of the following statements is correct about equilibrium constant? So A is also correct and D is also correct. Wait, what? No, that's question number 4, sorry. Question number 5 is this thing. Which of the, okay, reactions Kb may be equal to 2.9 10 power atmosphere. So over here it's from, oh, it's 2 gas to 3 gas. So yeah, it could be in atmospheric units. So A is in fact correct and D is also correct. So yeah, question number 5A is also correct. Why didn't I see that? I don't know. Maybe I just didn't see this D. Sorry, maybe I just didn't see the B over there. Something. I don't know. Okay. And then we have to go to question number 9. Which oxide of nitrogen is most stable? They gave D as the answer. Wait, what? But it has like 30 as the thing. So are these people that stupid? Seriously? Oh wait, I think this is a typo over here. Ah right. This should have 2 NO2, but so this is not like, what is this reaction? You can't have one nitrogen being two nitrogen suddenly, right? So there's a typo over there, and that's why, okay, that's why this was wrong. So okay, ninth, now we understand what went wrong. It wasn't our fault, it was their fault. They didn't give the whole question correctly. It's a typo over here. Question number 13. So when two reactants are mixed to give products, okay, the reaction quotient at initial stages of the reactants. So question number 13, I gave A as the answer, which is correct because it's almost zero, right? But they gave only D as the answer. So I think by initial stages they mean the first initial stage, and also some period after that. And maybe that's what they mean by initial stages. Or like maybe there's like some kind of fixed time limit which we call initial. I don't know. So yeah, like mathematically A is incorrect, but then come on, we are doing chemistry. It's approximately zero. So yeah, whatever. I mean, you let us use these equilibrium equations when there's closed vessels and all, even though we know nothing about what actually closed vessel does, right? We only know what gives energy. We know nothing about Hamilton's energy, and still you let us use that. So come on, you can cut us like some slack and say that yeah, it's approximately zero. It will work. Fine. Question number 13. It's just a misunderstanding basically. Question number what? Well, okay, that's it. All three questions we did. So yeah, question number 9, it's just wrong. So that's it. J main, window to J main, or get equipped to J main. It's done. So next time we'll do get equipped to J advanced. Right. So I'll see you guys in the next video.